So here is the lecture notes for the second half of 8.3. In this section, we're going to be looking at constructing a confidence interval for the mean when we don't know the population standard deviation. And we know that, for example, when we don't know sigma, when we don't know sigma, we use our best estimate for sigma, which is the sample standard deviation. When we use the sample standard deviation, this expression is no longer a standard deviation of the sampling distribution of X bar, but rather it is the standard error of the sampling distribution of X bar. And that's what we're going to end up using as we create the confidence intervals for what we think, an interval in which we think um, the population mean exists. Please remember that we have conditions that need to be met. We need to know that uh, the information collected came from a random sample, that the sampling distribution is normal, and we can achieve that by knowing that the population distribution is normal or knowing whether the sample size is large enough, 30 or more. And then lastly, we want to know that we meet the independent condition that is that if we're sampling without replacement, that our sample size is no larger than 10% of the population size. Nothing more to do than to jump into a problem. And let's take a look at the four-step process for constructing a confidence interval. A manufacturer of high-resolution video terminals must control the tension of the mesh of fine wires that lie behind the surface of their viewing screens. Too much tension and the mesh will tear. Too little, it will allow wrinkles. The tension is measured by an electrical device with an output reading in millivolts. Some variation is inherent in the production process. Here are the screen tensions for a random sample of 20 screens from a single day's production. Construct and interpret the 90% confidence interval for the mean tension of the screens from this day. So let's start out. Remember, this is an inference procedure. So we're going to talk about, well, what's the population that we're trying to make an inference about? And in this case, it is screens from a single day's production. What are we measuring about these screens? What's the parameter of interest? Well, it's the mean screen tension. And when units are given, we give them back, and that's measured in millivolts. We're done with step one. On to step two. We need the name of our method, our procedure, and this is a one sample T interval. And what do we want to do with this interval? We want to know what's going on with the population mean. So for population mean, we need meet our conditions. Our first condition is that the sampling needs to be random, and that is stated in our problem stem. We need to know that the independent condition is met. Now we're sampling without replacement, and our sample size is 20. And the question is, do we think 20 is less than or equal to 1/10 of the production of those screens in one day? And I think this is producing video screens commercially, that it is safe to assume the production for one day is at least 200 screens. All right, So we meet that condition. And then the normal condition. Now, the normal condition in this particular case, our sample size is 20, and we note that 20 is less than 30. So, and we're not told that in the problem stem that the population is expected to be normal. So this is a proceed with caution. But later on, we're going to talk about what we can do about that. All right. So, I'm going to put a star here because we'll talk about this uh, after we get some other tools underneath our belt. Let's go to the do step. And in our do step, we're going to say, okay, we need the confidence interval formula, which is X bar plus or minus T star times the standard deviation over the square root of n. Now, since the data was given to us in the form of raw data, I don't know yet the average or the standard deviation. So we're going to switch over to the calculator. Switch over to the calculator, and we'll open a new document, and we're going to put that data into a list in spreadsheets. And so we'll go up and say, well, we're going to collect data on these tensions. All right. And then from the data list, we can start entering in that data. Now, there's nothing more boring than watching me enter data in. So I'm just going to tell you right now, I've got the data already entered into another calculator document. So we're all done now putting the data in. What do we want of this data? We want to know the average and the standard deviation. So I'm going to add a page. In that page, it's going to be a calculator page. And from our menu, we're going to go to statistics, stat calculation, one variable stat calculation. We've got only one list of numbers. And that list is called tensions. So we're going to go ahead and get the summary statistics from that data. We see here that the average is 306.32, 306.32, and that the standard deviation, S sub x, is down here at 36.2093. So we'll use those numbers as we do our calculation. Let's go back to our 4-step and let's write down what we see. We see that the mean was 306.32. We're going to add and subtract T star. Okay, we need a T star value as well. See, we got 90% confidence, and our degrees of freedom is 20 minus 1, which is 19. So we'll be looking for the intersection between 90% confidence and 19 degrees of freedom. So 90-degree confidence is in this column. 19 degrees of freedom is in this row. And it looks like 1.729 is our T star value. 1.729 times that standard deviation, which we calculated, 0.362093, and that's all divided by the square root of 20. So as we go back to our calculator, and we'll calculate that confidence interval. So back to the bottom here. What did we have again? 306.32 minus our T star value of 1729 times the fraction with the standard deviation of the sample divided by the square root of the sample size. Square root of sample size being 20. So we get as a lower bound 292.321. And we get as an upper bound 200 or 320.319. All right, so let's put that onto our sheets. So the lower bound was 292.321, and the upper bound was 320.319. Let's go to our conclusion. With 90% confidence, we believe the true mean tension for screens from a single day's production. So we talked about what is it we measured and summarized, and what was the population that it came from, is between 292.321 and 320.319. And because units were given, we'll give back units. Those measurements are in millivolts. Okay, let's do that again for another problem. It says a principal at a large high school claims that students spend at least 10 hours per week doing homework on average. To investigate this claim, an AP statistics class selected a random sample of 250 students from their school and asked them how long they spent doing homework during the last week. The sample mean was 10.2 hours, and the sample standard deviation was 2.4. So construct and interpret a 95% confidence interval for the mean time that students at the school spent doing homework in the last week. So let's state again, our population, in this case, is students at this large high school. And let's say the parameter of interest for us is the mean time spent on homework during the last week. All right, our method, our procedure is once again going to be called the one sample. We're going to use T's this time. So T interval. And what are we trying to investigate? For population mean. We have our conditions that need to be met. For example, do we have random? And that was stated in our problem. So we meet the random condition. There's independent, in which we say n, which is 250, is this less than or equal to 1/10 our population size? And I'm going to say it is safe to say that the large high school has at least 2,500 students. All right, so we meet that condition. And then lastly, the normal condition. The normal condition, hey, our sample size is 250, and that's greater than or equal to 30, so we meet the normal condition. Great. Let's go on to our do step, reminding ourselves that the confidence interval is equal to x bar plus or minus t star s of x over root n. And in this case, our sample mean was 10.2. We need to know 95% confidence when there is 249 degrees of freedom. So we're going to switch over to our table. We wanted 95% confidence, so that's that column. And then we look here and we're like, wait a second. We don't have a 249 degrees of freedom to choose from. We have 100, we have 1,000. What are we to do? Well, what we're going to do is that we can't pretend we have more data than we actually have. So when we don't have a particular number on our table that we can use, we are going to use the smaller of the degrees of freedom that we do have access to. So in this case, we are going to use the 1.984 for our T star value. So there we go. We're going to use 1.984 as our best guess. Our standard deviation was 4.2 and our sample size is 250. So let's switch to the calculator and go ahead and put that in. 10.2 minus 1.984 times the fraction 4.2 over the square root of 250. So there's our lower bound of 9.673. Let's go up here twice. Change this to plus, and there's our upper bound of 10.727. All right. 9.673, comma, 10.727. And now we're ready to interpret that value. So we say with 95% confidence, we believe the true mean time spent on homework this past week for students at this large high school is between 9.673 and 10.727. Oh, units given, so we've got to give them back, and that would be hours. Follow-up question though. So based on this interval, what can you conclude about the principal's claim? Well, the plausible values from the confidence interval, the plausible values contain times less than 10 hours. So if asked, the principal would not be able to say that there are all the plausible values are greater than 10 hours, which is what his claims. Therefore, this data does not support the claim that on average, students spend more than 10 hours. All right. So moving on. Time to learn how to cheat. Well, cheat's a strong word. Time to learn that we have more flexibility than we think we might have. The T procedure are called robust. And they're called robust because even if a condition is not made, it still can give us good information back out. And in this particular situation, what we're going to focus on is the normal condition. When the normal condition is not made, for example, if we have large sample sizes grade 30, hey, we are okay. We're feeling really good. But one of the other things that was said was if the population is known to be normal. But if the population is known to be normal, how would we know? Well, one thing that we can do is we could look at our sample distribution, and maybe get an idea. If we get evidence of some normality, that combined with sample sizes that are big enough, then perhaps we have enough information to say, yeah, we kind of meet the normal condition, even though strictly speaking, we don't have a sample size greater than 30. So here's what we say. If the sample size is less than 15, which is pretty low, if the data appear to be normal in our sample, meaning relatively symmetric, single peak, no outliers, then we're going to say, we think we have enough evidence. Now, if the sample size is at least 15, we can tolerate a little bit of skewness, but we can't tolerate outliers or strong skewness. And then again, if the sample size is bigger than 30, anything goes. So let's go back to the screen tensions problem, and let's take a look and see whether we would have met that criteria. So here we are on the screen tensions page, and I might add a page so I can look at the screen tensions. Add the screen tensions here, and what do we see? Well, first of all, our sample size was 20. The dot plot does look symmetric. It doesn't look like it has skewness, and it doesn't look like it has outliers. To double check on the outliers, perhaps I can change this to a box plot. Yep, no outliers. Symmetric, single peaked. I think we're good. I think this gives us enough flexibility to say that if we went back to that old procedure and take a look at this procedure with caution, we might say, you know what, I'm okay. We could say the dot plot of the sample data shows no outliers or skewness. And we give ourselves a check mark on that old condition. All right, let's take a look at some of these conditions in some other situations and see if we can get some ideas here. Can we use a T? Determine whether we can safely use a one sample t interval to estimate the population mean for each of the following settings. So it's a histogram of the percent of the state's residents who are at least 65. Right? So we have this distribution, and if it's each state, that means we know that the sample size is 50. And at first blush, we'd say, hey, 50 is greater than or equal to 30. We look good on the normal condition. But then another thing says, wait, all 50? If we have all 50, that means we have a census. We don't have a sample. And if we have a census, we have no need to do an inference procedure. So any inference procedure is not warranted. Okay. How about the second one? It says a stem plot the stem plot of force required to pull apart 20 pieces of Douglas fir. Okay, well, you got 20. Well, 20 is certainly less than 30. And what our procedure says is that we could tolerate some small skewness, but not strong skewness and outliers. Well, boy, these look like outliers. So in this case, the stem plot suggests outliers and strong skewness. Right? And that in combination with our sample size means the T procedure is not appropriate. Okay. Let's look at this third one. Okay, sample size is 23. Okay, so 23, not 30, so we're not going to get out of this easily. But when we look at this distribution, okay, less than 30, okay, but the sample distribution, in this case, the stem plot of the sample has no strong skewness. I mean, there's a slight skew, but it's not strong skewness or outliers. And if that's the case, and if this is truly a random sample of these flowers that I can't pronounce, then I could say that the T procedure is okay. All right. Last one. You estimate the GPA of students at your school. You randomly select 50 students from classes you take. Here is the histogram of their GPAs. Okay. Well, if our population are students from classes that you take, then this is a random sample. Okay, so if the population are students in classes you take, then this is a random sample with a size of 50, and 50 is greater than 30. So we'd be okay. But if the population are students at your high school, if that's the case, if that's your population, then this isn't a random sample of those students. Oh, it's random, but it's not a random sample of all students. So if that was the case, then what you would have is T procedure not appropriate. Okay, so depends on how you define your population. So in this first one, the T procedure is okay. In the second definition, the population, the T procedure is not okay. And that takes us to the summary of what we've learned in section 8.3, where we've learned the new test statistic T. We've learned how to do confidence intervals with that T, and we learned about how to read the T table to find T star values.